Katangi tatiti, katangi takaka, katangi hoki koaho, tahe moriora. Ingamana, ingarea, ro rakatirama, tenakoto, tenakoto, tenakoto. Norera, ko waio, ko Harleen Hain takoingawa, ko te tumuaki o te wharewanaka o Otago aho. Na mihi nui kia koto, tenakoto, tenakoto, tenatato katoa. My name is Harleen Hain, and I have the great privilege of being the Vice Chancellor here at the University of Otago, and it is a great pleasure for me to be here to open this inaugural professorial lecture for Professor Ruth Empson. These lectures are really a time of celebration for the university community. They obviously provide an opportunity for us to showcase the internationally recognized teaching and research expertise of our staff. But more importantly, perhaps, they also provide a unique opportunity for our brand new professors to tell the story of their academic journey. And as we've learned over the years, these journeys often involve the very special people in their lives, people who contributed to their work and people who supported them along the way. And in my experience, it's these human stories that stick with us long after the lecture is over. The path to professor here at the University of Otago is not an easy one. In order to receive the promotion, the applicant must demonstrate excellence in teaching, in research, and in service to the university and to the wider community. As you will learn during the course of her lecture this evening, Professor Empson is a motivating teacher. She is popular with both undergraduates and postgraduate students. She also has an outstanding track record of research, and tonight we will learn more about her groundbreaking research on brain connections and behavior. And last, but certainly not least, Ruth has also provided outstanding service to her department, to the university, and to the wider research community. Ruth, on behalf of the University of Otago, it gives me great pleasure to congratulate you on your very well-deserved promotion to professor. And I will now call on Professor Vernon Ward, who will tell us just a little bit more about Ruth's academic journey to professor. Norera, tenakoto, tenakoto, tenatato katoa.
Thank you very much, Vice Chancellor. Tēnā koutou katoa, hame nui tēnā kia koutou. Welcome, everybody. This is Professor Ruth Empson's inaugural professorial lecture, and it's my task and privilege as Dean of the School of Biomedical Sciences to introduce Professor Empson to you this evening. So I'd like to thank you all for coming along on a nice warm evening with no air conditioning. An IPL is an important component of celebrating and recognising a successful academic career. So Professor Empson actually got her professorial promotion last year, but I believe she's been away for a year on research and study leave. So for anybody thinking that it's an out, it's not. You've been sure that you cannot escape from an IPL. For those of you who do not know, Professor recognising a successful academic, got an MA in Natural Sciences from Oxford University in 1988 before obtaining her PhD at Imperial College in the UK in 1993 in the field of neuroscience. So it was a 25-year journey for her from gaining her PhD through to professor. And it's a long journey. Along the way, she's held fellowships in Germany. She's also then went back to the UK in Oxford, Birmingham, and she had a period as a senior scientist at Cerebellar Limited in the UK. And I did have a little joke, but it's probably better I don't say it. So she spent 7 years as an academic at Royal Holloway in the UK before joining us here at Otago as a senior lecturer in 2007. She was subsequently being promoted to associate professor in 2014 before receiving her professorship in 2018. She's certainly earned her promotion to professor. She has an H index of 35. That's a very good H index for those that think of such things. Over 2,800 citations. She's published in prestigious journals such as Neuron, the Journal of Neuroscience, Journal of Physiology, and she reviews widely to a whole raft of quality journals. She's had substantial research funding as a principal investigator, including from the BBSRC in her time in the UK, the Marsden Fund here in New Zealand, and a whole plethora of different funding organisations over her career. She's very active in a whole raft of professional bodies, including roles in foundations and symposia and conference chairships, advisory committees, board roles, and all sorts of those sorts of things. And they're in places like for the Neurological Foundation, for the Australasian Neuroscience Society, the Brain Research New Zealand Centre of Research Excellence, and there's a long list beyond that. One area I would highlight is how active Professor Empson is in her outreach activities. She does a lot of public lectures, she does a lot of commentaries in the press, things like Ask a Scientist for the ODT is there, but she also does a lot of things with the discipline, speaking in the community, organising various organisation meetings in the community, talking to U3A, and these are on topics like movement, tremors, brain injury, things that are actually, many of us realise are really important. So she describes her research life as a journey of investigation into how connections in our brains work. These gaps or synapses are where information flow is transformed and also controlled. Understanding these connections and how they change is critical to understanding how our brains work and how they don't work. So for this inaugural professorial lecture, Professor Empson will explore her scientific and academic path, introducing and thanking people and celebrating the work they have done. She will take you on a journey from isolated synapse research 20 to 30 years ago to what's happening today in terms of studying synapses in living, awake and behaving animals. So it's quite the journey. With that, I'd like to invite Professor Empson to present her inaugural professorial lecture entitled Mind the Gap, Brain Connections and Behaviour. Nō reira, tēnā te mihi kia koutou katoa. Tēnā koutou, tēnā tātou katoa.
So thank you very much, Harleen, and thank you very much, Vernon, for this wonderful introduction. And thank you all so much for being here. I'm totally overwhelmed, and what a huge privilege it is for you to all be here, and thank you all very much for coming. So I hope what I'm going to do is give you a taste of the journey that my scientific career has been, and the title is a little bit of a play on words in terms of connections, because the part of the brain that I work on is those synaptic connections, but the connections with people have been, as Harleen was saying, is where I want to take you today and show you some of those very important connections. And no doubt I haven't and can't talk about everyone because, well, that would take me a very long time. And so there are, I hope that, if I don't talk about certain parts of my work, people won't be offended by that. So I'm going to start off with a map of the London Underground. And those of you who have travelled the London Underground will be aware of that voice that says, "Mind the gap." And they're talking about the gap between the train and the station. And I love this image of this map because it's a useful map, but it also makes me think about the brain and the stations along the way, the junctions, if you like, that you can take a new train at and go in a different direction. And our brains are full of these connections too, as we'll see, infinitely more complex than the London Underground, as if the London Underground wasn't complicated enough for some of us as well. So, but the thing about the London Underground is it takes millions of passengers every day from one place to another. And it does so under immense pressure, but it has all of these stations or places where you can change connections, and that builds in a huge resilience to this network. And our brains are immensely resilient to all of that we throw at them. And so these connections where you as a passenger can change or where information flow in the brain can change are fundamentally important. And so it's those connections that I'm going to talk about today. So what is a synapse? And I'm going to call it a synapse, showing my British accent. You might hear it as a synapse, but I'm probably going to say synapse for most of the time. It's a junction or gap between nerve cells where a nerve impulse, so this is nervous system information, your thoughts right now, are going across these synaptic gaps. And it's where that information gets transferred from one nerve cell to another. So it is a real physical gap. And information crosses that gap. And it's actually transformed as it crosses that gap. It crosses that physical gap. Electrical activity here at what we call the terminus. That's another transport analogy for you. The terminal here, the presynaptic terminal, gets transferred to this postsynaptic terminal via this transformation. And that transformation and what might be going on in that transformation has fascinated me since I started learning about neuroscience. And so why would I spend 30 years of my life thinking about these structures and these systems? Well, they're fundamentally important, and understanding them is fundamental for our knowledge of how the brain works, and we're a long way from understanding that. But the synapses within our brains are connecting the different parts of our brain that get recruited as you're listening to me right now. But synapses are also important for us to understand where our body is. We've got information coming from our bodies into our brain, and our brain is sending signals back out to our bodies. And the synapses and connections that make up all of that are critical to enable us to move, for example. So when we're thinking about synapses, they're fundamental for knowledge's sake, but in many or any neurological disease that you can think of, synapses are going to be altered and messed up in some way. So for that reason, they're important to study. So, mind the gap. I'm going to talk about a slightly different sort of gap now. There's a physical gap, and there's also a gap in time. And this is a recording from my PhD work, and I'm going to call it a squiggly line, for want of a better word. And I want you to remember this image for a little bit later on in the talk as this squiggly line. And what I'm doing in this work that I'm going to talk about a little later is I'm recording the electrical activity on this side, and I'm stimulating this side. And you'll see that there's something we call a baseline, and then you'll see there's a gap in time. This is time going along here. Very, very fast this is happening. And there's a short delay where nothing seems to happen. And then something happens. Squiggly line changes direction. Well, actually, everything is happening in this gap. In that gap, it looks as if nothing's happening, but it's that transformative process that is going on in that gap in time. So this gap in time is very, very important, and we'll talk about that. I'll bring that into something at the end of the lecture as well. So synapses, they're this gap in space, gap in time, and they're critical for information transfer. They're these junctions or connections. They're a kind of a go or no-go place where information is transferred or not transferred. A little bit like coming up to a junction in your car. Actually, you really should stop here, but you might not. You might decide that you're not going to stop. But hopefully you will stop, and there will be a decision as to which way you go. Or you might actually decide to just stay where you are. And the way that this works is with another key feature within neuroscience, which is something called the action potential. And what I'm showing here in the blue is a kind of an artist's impression of a squiggly line, that squiggly line that I just showed you. There's a little gap here. And when that squiggly line, when the size of that change goes above a certain value that is defined by natural and physical constants, an action potential is generated and is so-called fired. And that action potential is the means by which information travels long distances. But it has to be initiated by the synapse, by what's happening at this synapse. So information travels through our bodies down down effectively biological wires, both in and out of our brains, via this activation process, or this go, no-go system. And this is a picture of a cerebellar brain cell. It's one of my favorite neurons. We record from them in my lab on a daily basis, and they're so beautiful you can't possibly not fall in love with this beautiful structure. And they're beautiful because they also receive many, many thousands of synapses. The Purkinje neurons, they sit in the cerebellum. The cerebellum is at the back here of your head. And right now, you've got thousands and thousands of Purkinje neurons that are actually talking to each other and communicating with each other. And if we zoom in on this, and this Purkinje neuron actually puts out information down that wire when you make a movement or alter a movement or adjust a movement. So that's what the cerebellum is important for. And if we zoom in onto that neuron that looks complicated enough as it is, what we see is even more complexity. We see these little structures that are all individual synapses. So I showed you that sort of one-on-one individual synapse. I can't even count them all. So you start to see that my map of the London Underground is a vast simplification for what the brain might actually look like. So the complexity and beauty of the brain really fascinated me from the beginning of my research career. And it's been a huge privilege to be able to explore that beauty. And it all started with my PhD, I guess. And this is my supervisor, Professor John Jeffries. This is where I did my PhD at St. Mary's Hospital Medical School in Paddington. Some of you might recognize this, this image. If you follow Kate and William or any of the royal family, maybe nobody will own up to that. But the royal babies are all born in the Lindo wing at St. Mary's. And the Lindo wing is, I think, just around the corner from here. The department where I did my PhD is right here. It was a department of physiology and biophysics, and John took me on board. I was interested in learning more about neurotransmitters, ion channels, and he nurtured that interest in neuroscience in me. But I also wanted to just note that John himself has a very distinguished background. John is still active. He's in Oxford these days. And I was one of many of his PhD students. There's a whole list of them. And he himself was a PhD student of a neurologist called Tom Sears at the Institute of Neurology. And Tom Sears was one of many, many PhD students of Sir John Carew-Eccles. And Sir John Carew-Eccles, although it says ANU there, which stands for Australian National University, that's true, but Sir John Eccles was also in physiology at Otago. And he is Otago's only Nobel Prize winner. And although he didn't get his Nobel Prize when he was at Otago, he got it when he was at ANU, much of the work that he did towards figuring all of the stuff that he got the Nobel Prize for was done in physiology, in Lindo Ferguson building, in the basement, actually, where my labs are right now. So I feel this tremendous connection to John Eccles. And John Eccles himself was one of PhD students, many PhD students of Sir Charles Sherrington, who is one of my heroes. I have funny heroes, but he was a Nobel Prize winner for physiology in the early part of the 20th century. And I'll come back to Sherrington a little bit as well. So I don't want to presume too much, but you could maybe say that I was what? One of many great-great-granddaughters of Eccles, maybe? I'm sure he doesn't know that. Well, he definitely doesn't know that. So John nurtured in me this strong desire to understand circuits in the brain. We were working on a seizure model together, understanding epilepsy and what drives epileptic seizures. And I learned how to make these intricate recordings, getting tiny electrodes into single neurons and recording their electrical activity as they were doing things within their circuit. And this was a figure that John always used to show lots because he really loved it, because it's actually a very long-lasting seizure-like event that's actually happening within a bunch of neurons in a dish. But what I want to point out to you is that you'll notice that there are some squiggly lines here. And these are, if we zoom into those squiggly lines, we can see these shapes that look a little bit like that squiggly line that I showed you before, except now they're all happening together. There's a barrage of electrical activity that is happening at a whole large number of synapses that eventually results in the activation of this seizure-like event. And so my PhD was trying to figure out why this was happening. And I was very proud to get my paper published in the Journal of Physiology, which is still the most eminent physiology journal in the world, and long may it be so. It was the place we all wanted to publish at that time, and still do, actually. So after my time in London, which was wonderful and fascinating and challenging and all of those things, I was very fortunate to get a Royal Society Exchange Program Fellowship that took me to Germany. And I originally went to Cologne to work with a epileptologist, clinical epileptologist scientist, Uwe Heinemann. And I went to Uwe's lab because I wanted to learn more about how synapses change. And here we've got some more squiggly lines, exactly the same, but here we're modulating them with something called 5-HT. And 5-HT is serotonin. And serotonin is the chemical that is elevated by many antidepressant drugs. And these were in their heyday at this time when we did this work. And we wanted to know more about how they acted. Two remarkable people that I really want to say something about is that Dietmar was a student, and Andreas was a young postdoc in the lab in Cologne. And we all moved the lab about a year into my fellowship, which was perfect timing. We'd stripped the lab down and moved it in lots of trucks across Germany to Berlin, to the Charité, which was in the old eastern part of Germany. And remember, this is the time when the wall had not long come down, and it was a very exciting time, and a very challenging time, actually, to be setting up a lab. It was a lot of fun, and we worked very, very hard. And Dietmar and Andreas, we worked very hard together. I really learnt the great value of collaborating and working with other people when I was in Uwe's lab. It was a really important lesson. We're all a little introverted, aren't we? Or some of us are. Learning to work with others is part of the deal. You can achieve so much more. So Dietmar now heads up one of the most powerful and successful neuroscience centers in Europe at the Charité. Is an outstanding scientist and person, and Andreas is director of a Max Planck Institute in Heidelberg. So these are very, very important people, or talented people. And we were very productive, and that became very important for my career. But we were brought together by this man, who was very, very good at bringing people together, making people work together sometimes. And that was his great skill. And sadly, Uwe passed away 3 years now ago. But he was very, very important in my career. He was doing things, and I never even knew he was doing them. And that's actually what happens. That's the marvel of it all. And so a couple of years ago, Uwe was German, of course, and he had a great belief in forging German-Israeli connections. It was very, very important to him. And I actually benefited from some of those Israeli connections as well. And here we are at a kibbutz just outside of Tel Aviv 2 years ago. Here I am, here's Dietmar, here's Andreas. And we got together and we celebrated Uwe's scientific life, which was just amazing. And it just shows the esteem that he was held in. And what an amazing legacy of all the people all over the world who benefited from his mentorship. So I was enormously privileged to be there a couple of years ago. So the work in Uwe's lab was really, really powerful. It was really important. But I was interested. I was getting interested in what drives this transformation, what drives the synapses to work. And it comes down to calcium. And calcium, you'll know, is important in your diet. You have to make sure you take it in, and you'll think, oh, that's important for my bones. Yes, it is. It's also important for many, many, many other things. And not least is the triggering of these synaptic events. So I wanted to learn more. We did a little bit of this with Dietmar in Germany, and we used a very old technique, which was to look at extra. So we were looking at calcium not in the terminal, which was where I really wanted to look at it, but outside. And calcium is at a high concentration outside of living cells, and at a low concentration inside living cells. And calcium can enter the cell or enter the compartment, such as this terminal. It goes through channels that allow it through. And what we did was that we actually measured the outside calcium. Here, there's a little trace here, another wiggly line, slightly different kind of wiggly line, but what we showed was that serotonin was actually decreasing the calcium signal. And that was part of how it was acting. But this was a very, unsophisticated way of looking at this problem. And I wanted to actually be able to measure the calcium inside the terminals. And towards the end of the time that I was in Berlin on my fellowship, I actually suffered a quite serious health setback. I became incredibly allergic to laboratory rodents, which is a bit of a problem. You might say that they got their own back, but it happens to many people, and it was largely due to some of the conditions we were under in Berlin, because things were very chaotic. And so my immune system needed to have a rest from being close to laboratory animals. And there were people who said, oh, well, that's the end of your career. You can't do it anymore. And I didn't really want to listen to that, obviously. And I was very fortunate to actually find a way through that actually turned out to be even better than I could have imagined. Because I learned how to measure calcium using some of the really modern techniques that were around at the time, using something called calcium-sensitive fluorescent dyes. And I went back to Oxford, to pharmacology in Oxford, and I worked with Anthony Gaglione, who is a very, very smart man, and now he was head of Department of Pharmacology for 9 years, and has now just got a Wellcome Trust senior investigatorship that gives him time to just focus on his research. He's a very, very smart guy. And I benefited hugely from working with Anthony, even though I was working on, of all things, sea urchin eggs. And what you see here is a sea urchin egg at the moment of fertilization. So the sperm has bound to the egg here, and there's a calcium wave that crosses the egg. And the mechanisms that are involved in that calcium wave are actually also present in many, many other cells. They're primordial mechanisms that are fundamental for calcium handling in neurons, hearts, eggs. And also we did a little bit of work in synapses towards the end. And that period of time in Anthony's lab was enormously productive at gaining publications in what we call high-impact journals. This was a very hot field, a little bit like this lecture theatre. It was a very hot field, and it was competitive, and we were there amongst that competitive field. And it was really, I guess, those papers plus the productivity that I'd had in Uwe's lab working with Andreas and Dietmar that really was the foundation for getting my first academic position at Royal Holloway. And as I said, this was a competitive field. And as a young scientist, you can't necessarily play with the big boys because this is just a little bit for the young scientists among the audience. And I decided that I needed to look at the problem from a different angle than everybody else. And so I decided to look not so much at what was happening with calcium coming into the cell, but what's happening when calcium goes out of the cell. So the fact that calcium at a high concentration can come in to the cell where there's a low concentration of calcium is something we call a chemical gradient. It's like a downhill. Calcium goes downhill along its chemical gradient and easily gets into the cell. But if there's too much calcium in this compartment or in this cell, things can go wrong, and it has to be got back rid of. And if you've ever skied, you'll know that to have this, you have to go back up the hill at some point. And that takes energy, or you can take the chairlift, which also takes energy. So my niche that I started to dwell in and to learn in when I went to Royal Holloway as a young academic was to look at what this getting calcium out of the neuron was important for. And again, I was really, really lucky because I was able to collaborate with other people on this kind of question. And this is us getting £400,000 for our neuron project. This was a big deal in 2001. Still seems like quite a lot of money. This is the on-campus. And my auntie died last year, and I cleared out her house, and she had saved this. So we're thankful for all the people for saving real pieces of paper. I think we should learn from that. So here we are. This is Philip Beasley, myself, Mark Crompton, and George Dixon. And we had this collaborative grant, which was really pivotal for the beginning of my scientific career, my independent scientific career. And I was also lucky to get some good students. And I'll talk about a few good students. So this molecule here, PMCA, this doesn't roll off the tongue very well. But this is like the ski lift taking you back up the hill. This is the molecule that gets calcium out of cells and is important for controlling the calcium inside the cell. And Tom Jensen, who's now a research fellow at University College London, Queen's Square, very talented, hardworking young PhD student. He's at the Institute of Neurology now, which is a very prestigious institution in London. He set out to look to see if he could find this protein, this mechanism at synapses. And he found it at the presynaptic terminal and not on the postsynaptic terminal. So it's perhaps important for controlling the calcium that's going to be that trigger for the synapse to work. And what he also showed is that it was this protein, this PMCA, chairlift, doesn't matter what it is called really, that it was important because it was enriched or at greater levels than we might expect in presynaptic terminals. So he set about looking at what the impact of this protein might be. And we've got some more squiggly lines here. They're going in a different direction. That's just technical. But what you'll see is these events here are marked by these little bars. These represent that transformative process. Within that little squiggle, the transformative process at the synapse is happening. And when he blocked this molecule, I think you'll agree if you look at the red squiggly lines that there are more of them there. And so this told us that, this was important for the way in which the synapse would work. And this was great, and Tom got a great publication out of it, another Journal of Physiology paper, and he was happy. But I wasn't particularly happy because we didn't know how this relates to behavior. How does this relate to behavior? What's the point of all of this? And this is where another very important connection became clear. In the literature, it had been shown that this PMCA was, when you removed it from an animal, the animals developed an ataxia, a movement disorder. And this gave indications that this was important. And it had also been shown that the PMCA was very highly expressed in the cerebellum, that area of the brain back here that is important for movement. And so I wanted to study synapses in the cerebellum. And I wrote to this man, Thomas Knopfel, who was in Japan at the time, and I wrote to him and said, please can I come to your lab and learn how to record synapses from the cerebellum, thinking I would never hear anything more. And he wrote back and says, yes, of course you can come. When do you want to come? So I went to Japan and I learned these techniques as a young academic. And I learned how to record calcium in presynaptic terminals, which is what I had been wanting to do. And these presynaptic terminals are these so-called parallel fiber synapses. They're like railway tracks, more railway analogies, and they run the full length of your cerebellum. And along these little railway tracks are these synapses that I was going to study. So what I did was I learnt how to measure that presynaptic calcium. And what I'm going to show you is, this is where the fluorescent dye, we use the fluorescent dye to monitor the calcium, and we fill the railway tracks with that dye. And then we can stimulate those synapses, and you have to be careful if you don't miss it. And that is that rocket-like signal is a presynaptic event in those terminals. There it goes. And what we showed is that the behavior and the kinetics of those terminals and the way in which calcium was being handled in those terminals was slower. I won't go into the details. And that this might be really, really important for why these mice have this cerebellar ataxia or movement disorder. So we were at the start of linking the biology or the synapse physiology with the behavior. So this got me interested in spinocerebellar ataxias, which are a rare movement disorder seated within the cerebellum, within the part of the brain I've talked about. And they're a rare disease. And I'm going to say something about rare diseases because rare diseases can often illuminate things that we wouldn't see in a more widespread disease. And it's a reason why we should study them, because we can learn new and important things from those rare diseases. And of course, they're not well treated either. So I'm just going to play you a little clip, it's not very long, of someone who has ataxia.
It's happened to me a few times, people thinking that I was drunk. I was getting in my car in Brighton, and I was getting in, and a lady came over to the car, put her hands to stop me pulling away, and just said, "You can't drive in that condition." I then sort of got out my disabled badge and said, "What, my disabled condition?" Ataxia is a degenerative neurological disorder which affects your balance and coordination. Obviously, there's some things that I can't do, like I got to get things off high shelves, and taking hot things out of the ovens, it was a bit of an issue. Yeah, I'm okay. I'm still driving around. I just sit down a lot. As far as the future goes, I really don't know what to expect. It could be a case where I stay at the same level, or it could be a case where I get a lot worse quite quickly, but only time will tell, really.
So that gives you a glimpse into the life of someone with ataxia. Oh, no, we won't listen to it again. Nope. So we were fortunate when I came to Otago to get, again, through a collaboration, to get access to a mouse model of ataxia, a different one. And this is where another talented PhD student, Emmett Power, comes in. So Emmett started working on this model. And here's Emmett. So Emmett got his PhD a couple of years ago, and his other great achievement in the last couple of years is Ronan sat here. I don't know if Emmett's here, maybe not. But so Emmett and Nicole and Ronan. So Emmett started looking at the synapses in this model. And what he noticed was that a particular type of action at actually these railway track parallel synapses were overactive. That's unusual in a neurological disorder. We tend to think of losing things rather than gaining something. And so this was quite important in the field. It's become a little controversial in the field, but these animals in the early stages of their ataxia, when they're not very behaviorally compromised, they have these altered the timing of these connections is altered. And Emmett went on then to try and understand what was behind this, and of course it came down to calcium again. So that's a little what Emmett is doing here. He's recording from a Purkinje neuron, and he's stimulating those railway tracks. And if you didn't catch it the first time, there it goes again. So a very local area of that neuron is the calcium is elevating in that cell. It turns out that that calcium is probably what's driving some of the neurodegeneration in this disorder. And we took that work forward and actually were able to rescue the behavior in these mice with a drug that just tweaked down that overactivity. And Mohammed, and I won't go into the details, but Mohammed in the lab, who's a PhD student, has been working on that problem for about 3 years. And we've had an immense luck and to get money from Roche to help us do this. And you'd learn just how long and how complicated it is to start developing drugs for real use. So Roche has a rare diseases group, and they focus and put funding around the world to look at these rare diseases because they value their importance. And we're a long way at the moment for trying to get this drug into patients, but we're still trying. So in the last few minutes, and Mohammed has got that task, in the last few minutes, I want to go back to Sherrington, my hero. And Sherrington was a great physiologist. And towards the end of his life, he wrote a philosophical book, which is highly poetic and actually way beyond me, to be honest. And in it, he has a vision about seeing electrical activity in the brain, something that he couldn't even comprehend as reality in the 1940s. And this is an artist's impression of what came to be known as Sherrington sparks art. So what you're seeing here is lighting up of these synaptic connections. And Sherrington was saying, what would the brain look like if we could see the activity? And we've actually been working on this problem for the last 4 or 5 years, and largely because we've been very fortunate to work with Thomas, and this is where he's been incredible again, and working in a collaborative manner internationally. And so Thomas was working at Riken Brain Science Institute in Japan. A large amount of money being allocated to research into the brain, and he has spent 25 years developing a means of seeing electrical activity in the brain, and it's come to fruition and is continuing to come to fruition. So Thomas had developed this so-called sensor. So instead of me putting tiny electrodes into single neurons with painstakingly and frustratingly amounts of time required, we can now image, just as we have been imaging that calcium, we can image electrical activity. And we were fortunate to get collaboration with the Allen Institute for Brain Science in the US. All of you will know who Bill Gates is, I'm guessing. And Paul Allen co-founded Microsoft. And Paul Allen put an enormous amount of his philanthropic money into developing pipelines for understanding the brain. And we were lucky to get onto one of those pipelines. And sadly, Paul Allen passed away, I think it's last year or a couple of years ago. And so we developed, the Allen Institute developed a mouse. We got access to that mouse, and we've started working with it. And we are now doing work in mice that are awake and behaving and doing things that I'm going to show you. Javier here is, we call Javier the mouse whisperer, because he can train mice to do things and train them to sit still and train them to do things that he wants them to do. It's a very big skill. And Dan here is also a bit of a mouse whisperer on the quiet, but has been important for developing all the computational tools that we've needed to do this work. So we are imaging the mouse brain through their skull. So we're not, the skull is intact, the mouse is imaged, the brain is imaged, and the mouse is awake. And I'm going to show you one of our really exciting maps. So the mouse gets a little vibration to its paw. It's a bit like you feeling a haptic feedback on your phone, just like that. Not at all painful, or just a little stimulus. Very short. We call it light touch. And what you're looking at is the nose here and the tail here. And something happened. That was the light touch. I'll play it again. So what we're seeing is a spark of activity, maybe something like Sherrington's spark, in the brain of this mouse as it's perceiving that light touch. So this is a brain signature for a perception. And we think that's very, very exciting. You may not, but I definitely do. And what I'd really like to say, coming back now, remember that squiggly line I showed you right at the very beginning? When we look at the time course of those events that I've just showed you in the living awake mouse, there's a baseline. There's an activation, which is when the light touch happens. And then there's a gap. There's a space in time before the activity happens. And of course, what's happening in this space of time is the activation of those connections that I've just been talking about. So we are now seeing real connections at work in a real living, awake, and behaving mouse. And that is for us, and for neuroscience, actually really rather important. So I hope I brought you full circle from an old-fashioned style of work to something that's very new and hopefully is really groundbreaking. And not too many people have seen these light sensation touch maps. So it's a real privilege to be able to show them. And we've pioneered all of this here at Otago, and it's been really fantastic. So I don't want to drone on too long, but I do just want to say a little bit about people, if my computer hasn't frozen. There we go. So I think it's really important that that I thank my parents for bringing me into the world. There they are. And that's probably the only time you've ever seen me in a dress. It's a bit of a weird dress, but anyway, I liked it. Yeah, I'm very grateful for my family for bringing me into the world. I'm also very grateful for other families along the way that have been really pivotal as well. Not least my scientific family that I've just talked about. This is probably the only photo that you'll see me wearing makeup. So it is me, I promise. Just the teeth you can see. This was on a Reserve Forces Army training commissioning course, actually. And this is a general purpose machine gun. So I don't know how many IPLs have got where you're faced with a GPMG. Anyway, somehow I always ended up carrying it. And this is another part of that Army family. So I was 18, did that for 18 years. And yeah, I think I look about 12 there. And probably there as well. So the Army family, shared values, shared connections, different life completely was very, very important to me as an academic. Trying to understand that people outside of academia are a little bit different and think about things differently. And here in Otago and here in Dunedin, I'm really privileged to be part of two church families, and it's really wonderful to see my church family here today, both at St. Paul's and at All Saints. And if you want to understand what Taizé chanting is, we do it on a Sunday night, and you'd be very welcome at All Saints. And of course, to my Rotary friends, and again, I am very, very grateful to the Rotary people that I can see. Thank you for coming as well. And I'm just going to, yes, education. I'm the only person in my family to go to university, and for me, education was a very powerful force. And I think Senator Fulbright said that education is a slow and powerful force, and it is, and it always should be. And I feel enormously privileged to be in education, being able to maybe influence a few people along the way, as people influence me. And it's really important to hold on to the great value and empowerment that education brings. So I'm just going to finish there with some acknowledgements, all the various organizations and money that has powered this work over the years, which I'm immensely grateful for and take very, very seriously, comes out of people's pockets. And we should treasure it and use it well. And I'm going to now leave with a few names, hopefully, that come. So just family. We started with the Capels, and we're ending with the Greenstone. And family there, school teachers, university, Army, some of those not longer here with us. Some of you might see your name, some of you might not. If you don't, then you know who you are. And physiology, mentors and colleagues, very, very important at my time in Otago. And internationally too. With that, thank you very much.
Cool, okay, got it now. So as I said, my privilege to be able to thank Ruth. It's an enormous event for her to tell us about her journey, and for one, I've really appreciated it. I've learned quite a lot about Ruth, things I didn't know, whereas I felt I knew her relatively well. You've showcased a lot of your strengths, and I just want to spend a couple of minutes kind of gathering together those strengths that you've shown us through your talk. First, your passion for neurophysiology and how that came full circle, as you've said, from when you were a student to now where you're pioneering new techniques. Another big one is kind of tackling the big questions. Ataxia, it's maybe rare, but as Ruth said, if we can find out what's happening at the molecular level down in the brain, then that will help understanding the brain and other disorders. But Ruth doesn't tackle it from one angle. She's a physiologist, she's a great, does a lot of traditional electrophysiology, but she combines it with molecular approaches, dynamic imaging, as you saw, whole animal behavioural models that you've seen, and a lot of computational analysis behind it. And of that package together is the real strength of Ruth's research. Ruth's an early adopter of novel and often untested technology, and she showed us that through that collaboration with Thomas Knopfel, and that's been carrying on for a decade or more. And she's shown us today with that light touch image, that's using that technology, and we should be very proud that she, as she said, she's pioneering it here at Otago. She's able to do that work here. With the help, I should add, of all these people that she has mentioned. She has a large lab, and they're all very committed to that research. Finally, I think as an audience, we've seen Ruth's really powerful scientific communication skills. Professor Ward mentioned previously, Ruth's invited to give public lectures where she can break down this really quite complex physiology to something that is accessible to a public audience. Not only with community groups, but she's had a long history working with Brain Day, working with students, high school students, for example, who come into the university, International Science Festival and so on. She really takes it quite seriously that as scientists we need to be communicating with the public and helping them to understand where their tax dollars go to support us in our research. So please join me in thanking Ruth again for a really great IPL. Very important event next. We can't let this occasion go without some commemorative gifts. So Ruth, would you be able to come and accept those? So this is on behalf of the university and the Department of Physiology. And I'd like you to note the butterfly paper. So thank you.